Hello, my name is Büchi Automata,
And I am Ondřej Lengau.
and we would like to tell you something about our work, which is devoted to optimizations of rank-based Büchi Automata complementation.
Büchi automata are a well-known formal model for describing infinite words. A Büchi automaton over some alphabet sigma consists of a finite set of states, a non-deterministic transition function, a set of initial states, and a set of accepting states. The automaton accepts some infinite word by starting in some initial state and then looping over accepting states. It is well known that Büchi automata correspond to the class of omega regular languages. Here we have an example of a Büchi automaton that accepts the word ABBA omega, and the accepting run in this automaton can, for example, be by starting in R, then over A staying in R, over B going to S, then over the next B going to T, and then staying in T over A. T is an accepting state, so this word is accepted by the automaton.
As motivation for Büchi Automata and Büchi Automata complementation, we mentioned three fields. The first one is the model checking of linear time properties, where the property and system both are represented by Büchi Automata. And then checking whether the system meets the property is equivalent to language inclusion checking between the automata, which is equivalent to emptiness checking of the intersection of the first automaton with the complement of the second automaton. The second field is a termination analysis within the tool ultimate automizer, where the complementation is used to construct a difference automaton that removes traces where the termination argument has been already established. And the third field are decision procedures for logic such as S1S, ETL, QPTL, and so on. For example, for S1S, complementation is used to implement negation.
Büchi automata complementation is significantly more involved than complementation of finite automata, because Büchi automata cannot be easily determinized. The lower bound for complementation of Büchi automata is 0.76 n to the power of n, which was achieved by Yen in 2006. Over the years, many Büchi automata constructions appeared, for example, based on the Ramsey theorem, determinization-based, rank-based, and so on. In this talk, we focus on rank-based complementation, where the state-of-the-art was achieved by a series of papers by Kupferman and Vardy in 2001, Friedgut, Kupferman and Vardy in 2006, and Schewe in 2009.
The rank-based Büchi automata complementation is based on the notion of rundac in the automaton over a given word, which represents all runs on a given word in the automaton. The vertices of the rundac are pairs where the first item is a state and the second is a level in the rundac. For example, consider this automaton, then the rundac over the word B omega you can see here. And if we want to check whether the word is accepted by the automaton or not, we can assign numbers or ranks to each node. By the following ranking procedure. We start with I equals to 0, and in the first step we assign rank I to vertices with finitely many successors, and we remove them from the rundac. And in the second step we assign the rank I plus 1 to vertices that cannot reach some accepting state, and we again remove them from the rundac. And this we increment the value of I, and we repeat it while this condition holds. Consider this in this rundac. These nodes have the rank 0 because there are only finitely many reachable successors. Then these nodes have rank 1 because they cannot reach some accepting state, and finally this single node will have rank 2. And as already proved, Kupferman and Vardy in 2001, if a word is not accepted by the automaton, then every node in the rundac has rank at most two times number of states after this ranking procedure.
In the complement, every macro state corresponds to a level in a rundown. The macro state is a quadruple SOFI, where S tracks all runs of A in the same way as subset construction of finite automata. O tracks all runs with an even rank since a breakpoint. So the O serves as a breakpoint, and in order to accept some word, we need to decrease the rank of all states and thus clear O infinitely often. F is a ranking that guesses the ranks on some level of the rundown. We focus on tight rankings, which are defined by having an odd maximum rank and cover all ranks from 1 to the maximum rank. The transition function of the complement is composed such that the S part is obtained by subset construction in the same way as in finite automata. The breakpoint, that is the O part, keeps successors of O with even ranks. So if some successor has an odd rank, it is removed from O. And F is a non-increasing tight ranking, which is consistent with the transition function. The complement contains of two parts. A part that we call weighting, which is pretty much a subset construction of the finite automaton substructure of the Büchi automata, and non-deterministic transitions into a tight part, which contains macrostates of this form and where each ranking is tight.
As an example, consider this automaton, the complemented automaton with a highlighted weighting, and the tight part is you can see here. If we consider, for example, this macrostate, and we want to get all successors over symbol B, then S prime part is a set of all successors of ST over B, which is the set ST. The restrictions for the ranking function you can see here. The only possibility is this ranking function, and the O prime part contains states with an even rank, which is T. So the only one successor is this macro state. Yeah, you can see here. Similarly, the reverse direction, if you want to go from this macro state over B, we reach only one successor, which you can see here.
The rank-based complementation approach has two main problems. The first problem is that the automata obtained are highly non-deterministically. We need to non-deterministically guess when to switch from the weighting to the tight part, and in the tight part, we need to non-deterministically guess how to decrease the ranks. This yields many different successor states when the tight part is constructed. Moreover, the tight rank bound, which is computed as twice the number of states minus 1, is often too coarse. This is often unnecessarily high, and many redundant states are generated, the states which are not actually needed in the complemented automaton. This causes state space explosion because the number of states combinatorially depends on the bound B. The optimizations that we will show later show how to reduce the non-determinism and how to keep the ranks as small as possible and thus obtain smaller automata. The optimizations are lightweight, and they are based on the notion of super tight runs. A super tight run is a run of the complemented automaton of some word which uses as small ranks as possible. In our optimizations, we guarantee that the super tight runs will be preserved, and only some runs which are not super tight might be removed in the complemented automaton.
Our first optimization, called the delay optimization, is based on an observation that more super tight runs over a given word can differ on the position of the transition from weighting part to the tight part, as you can see here, and we can keep just one of them. Therefore, we can postpone transitions to the tight part in a way that we generate transitions to the tight part only when a cycle is closed in the weighting part, which is similar to the condition in partial reduction. Consider this automaton. Then the weighting part of the automaton is here, and the original Schewe procedure would generate transitions to the tight part from all these macro states. However, we postpone generating transitions to the tight part from macrostates P and PQ, and we generate transitions to the tight part only from the macrostate PQR. Therefore, we can reduce the number of transitions to the tight part.
Our next optimization is called subrank because it decreases the rank of some macrostate based on its successors. It's based on reasoning about the waiting part of the automaton, which defines the skeleton of the tight part because it is defined the S part of the macrostate. We can use the structure of the waiting part to restrict the maximum rank of some macrostate, for example, by observing how big are the maximum infinitely often reachable macrostates. For example, if we have from some macrostate several lassos reachable, we can restrict the maximum rank of the macrostate here by the sizes of the maximum infinitely often reachable macrostates in some loop of the lasso. Consider the example of this automaton, which has two separate parts. In the waiting part, it looks like this, and you can see that from QS, the maximum size of an infinitely often reachable macrostate is 1 because it's only R. So we can remove any macrostate from the tight part where the macrostate Q and S is assigned higher rank than 1. For example, here, we can see that we have two macrostates when R is assigned 3 and here T is assigned 3. This is not necessary because the maximum rank necessary is only 1. So we can remove these two macrostates.
The previous optimization we can refine with a minimal infinitely often reachable macrostate. Consider some macrostate SOF and some state Q from S. Okay, we have an S, and with some maximal infinitely often reachable macrostate, and some state Q with minimal infinitely often reachable macrostate. Then only these states can have higher rank than FQ. In other words, the difference between the maximal infinitely often reachable macrostate from S and the minimal infinitely often reachable macrostate from Q give us the number of states with a higher rank than FQ, and it allows us to reduce the maximum rank of a macrostate in this way. Consider this example. The part of the complement is here, and consider this macrostate. Then the minimal infinitely often reachable macrostate from R is RT with a size 2. Therefore, the maximal rank of this macrostate can be bounded by 3, and which is not the case for this macrostate, and hence this macrostate is redundant, and we can remove it from the automaton.
Our next optimization is called rank sim, and it is used to impose a relation between ranks of some states inside the macrostates, and this relation is based on some notion of simulation. For each macrostate in every supertight run, it holds that if two states in the macrostate have an odd ranking, for example states P and R, and some simulation-based relation holds between the two states, then we can deduce that the rank of P needs to be less or equal than the rank of R. The relation is called odd rank simulation, and I will not go into technical details because it's quite involved. I will show an example where this helps. So suppose we have this automaton and we are exploring the macrostates that contain the states Q1 and R1. We computed that the Q1 and R1, the relation holds in both ways. So Q1 is odd rank simulated by R1, and also R1 is odd rank simulated by Q1. So from this formula, we can deduce that the ranks of these two states need to be the same. So we can remove all macrostates where the ranks are different, like here. We compute with an under approximation of the odd rank simulation, which is computed as some least fixed point, starting with standard direct simulation on the automaton.
Our last optimization is called the max rank optimization, and it's inspired by reduced average Audi reconstruction by Schewe. And this optimization represents several runs, including super tight runs, using a single maximal run. In a way that the ranks of the macrostates in the maximal run is bigger then the ranks of the corresponding macro states in the subsumed runs. And it's used to reduce the number of non-deterministic choices, because if we generate successors over a given symbol, then we either decrease ranks of all possible states in the O set. Okay, as you can see in this example, where we decrease the ranks of states in the O set, or we continue to the maximal macro state. Okay, it's this choice. And we use this optimization in addition to the previous optimizations.
Let us say a few words about the experimental evaluation. We took the random automata over a 2-symbol alphabet, which were obtained by starting with 15 states and randomly adding transitions. The benchmark is from the work of Tsai, Fogarty, Vardy, and Tsai. We reused the automata using Spot and Rabbit, and then we removed semi-deterministic, inherently weak, unambiguous, and automata with empty language, because for those we can have a more efficient complementation procedures. We were left with something over 2000 automata for which complementation is hard. The timeout was set to 5 minutes. We implemented our approaches in a tool called Ranker, and we also have a combination of Ranker and Peterman's algorithm. Where we construct the weighting part of the automaton, we can see from the rank estimates that the complement would probably be too big, and we can do some kind of safe degradation into using a Peterman. We compared our approach with goal, where there is an implementation of Schewe's construction with the reduced average out degree, Safra, Peterman, and the Fribourg construction based of subset tuples. And we compare with Spot, LTR2D star, Seminator, and Roll. So we took all the state-of-the-art tools for complementation.
In the first experiment, we compared our procedure with the best rank-based complementation procedure that we know of. It's a Schewe reduced average out degree implemented in goal. We were interested in the size of the generated state space, therefore we use no post-processing. And from the graph you can see that that we are in many cases, almost all cases, we are better. This part is the part where we are better, and know that the axes are logarithmic. And you can see that we save significant part of the state space.
In our next experiment, we were checking how small automata we can compare by various approaches. So we were using post-processing of the obtained automata by outfill from the toolset of Spot. In this experiment, we were focusing on determinization-based approaches, and we took Peterman implemented with goal, which on average performs better than Safra, Spot, or LTR2D star in the sense of the number of states of the complement. You can see that we are still above the diagonal, so we perform better. However, in some cases, we also time out. The timeouts are on the line in the right.
We also show our comparison with Seminator on the left and with Roll on the right. Seminator is based on the semi-determinization based complementation procedure, and the Roll is using learning based approach. From the graph you can see that compared to Seminator 2 we are in many cases better. And on the graph on the right side, you can see that in some cases Roll is performing better than we do. However, the Roll has much more timeouts than we have.
Let us give more details about the experiments. First, let us focus on comparison of rank-based procedures. Here you can see that our procedure was actually quite better in almost all of the cases when it finished, with the exception of 3 cases where 2 of them are due to timeout. Also, the median obtained by us is much smaller than the one obtained by Schewe's procedure. The mean is a little bit higher, but that is due to the fact that we did not time out so often. So we actually obtained sometimes quite large automata, and we think that even bigger automata would be obtained if the Schewe's procedure implemented in Go would terminate on such inputs. For the other experiment, where we were comparing the sizes of the obtained automata, you can see that Ranker has the lowest mean, with the exception of roll. Roll is a learning-based procedure, which is actually learning the complement language. It often has obtained smaller automata. The problem is that it timeouts on almost 50% of the benchmark. Further, you can also see that the median for us is again the lowest, with the exception of roll. In the right-hand side of the table, you can see that for all of the tools we actually won, which means we obtained a smaller automaton, then we lost, which is that we obtained a strictly larger automaton than the tool. Let us note that for our basic procedure implemented in Ranker, we have quite some timeouts, something like 15%. When we combine with the Peterman's procedure by the way of checking the size and the ranks from the waiting part of the automaton, we could put the number of timeouts quite low to something like 0.7%. Further, let us know that in something like 22%, we obtained a strictly smaller Büchi automata than any other procedure, and in 63%, we obtained at least as small BA as any other procedure.
In our work, we have proposed series of optimization reducing the state space in rank-based Büchi automata complementation. Based on our experiments, we have shown that we are competitive to the other approaches. In particular, in 22.5% of cases, we are strictly better than other tools.
In future, we wish to get more precise rank estimations according to the automata structure. We also wish to generalize our techniques to transition-based generalized Büchi automata and also to Emerson lane automata. And we want to also use our techniques in language inclusion checking of Büchi automata. Thank you for your attention, and if you have any questions, please don't hesitate to contact us. Bye-bye!